Hello, this is Math 125, week 3, uh, lecture 3. So today let's start with the definition. So remember we were discussing functions, right? We have seen examples of functions. We have this vertical line property, right, for the graphs. We know how we can decide a given subset of some Cartesian space, right, set, or Cartesian product of sets, whether or not the given subset is a function or represents a graph of a function, right? So we have seen this. Let's now define one-to-one functions. So a function, let's say f, remember this notation. S is the domain, T is the codomain of f. F is the symbol of our function. A function, such a function is called one-to-one. One-to-one. Each time writing 1 dash 2 dash 1 is very hard, right? So let us introduce the following notation. Whenever I write 1 dash 1, that means 1-to-1, right? Okay. A function is 1-to-1 or simply 1 dash 1, 1-to-1, right? Um, 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 if distinct elements in S have distinct images in T. If distinct elements in S have distinct images, right? Distinct images in T, right? The image values of F are taken in the set T, right? Distinct images in T. So this is how we define one-to-one functions. Equivalently, that is I dot E dot, that is if maybe I should write like this. That is, let me write the whole phrase. F is 1-to-1, right? If and only if the following statement is true. If x1, x2 in S, right? Whenever we take two elements of S, distinct elements, right? Whenever x1, x2 in S, and they must be distinct, so x1 is different than x2, right? X1 is different than x2, then their images must be also different. Okay, so this is the definition of a one-to-one function. Okay, so there are some other equivalent ways of equivalent conditions for one-to-oneness, right? Or equivalently, equivalently, let us consider the contrapositive of this, right? So this statement holds if and only if contrapositive holds. What is the contrapositive of this statement? Equivalently, f is 1-to-1, right? If and only if whenever x1, x2 in S, whenever we pick two elements in S, and we are trying to write the contrapositive for this. So this is like P implies Q, right? P implies Q. So not Q implies not P. This is the contrapositive of the statement, right? but x1, x2, they are always taken from the set S, of course, right? So this is common assumption. Here is the right. We consider the contrapositive for these propositions, right? For this, if x1 is different than x2, then f of x1 must be different than f of x2. Therefore, when we consider the contrapositive of this condition, right, of this statement, we have the following. Whenever x1, x2 in S and f of x1 is equal to f of x2, then if two things have the same images, then they must be equal to each other, right? This is exactly the contrapositive of this, right? So if two elements have the same images, then they must be the same, right? So this is some equivalent way of describing describing one-to-one function. In terms of graphs, we have some other alternative description in terms of graphs. In terms of the graph of f, right? In terms of the graph of f, we have the following. In terms of the graph, remember, graph of f, right, is denoted by this, right? G sub f, right? Graph of f. Um, we have. This means that. Okay, another equivalent, right? Different but equivalent, of course, right? Condition for one-to-oneness, right? Any of these, you can check any of these conditions to show a given function is one-to-one, right? So, what is the equivalent description in terms of the graphs? F is one-to-one if and only if for each. Remember, this is a subset of S cross T, right? So this is a subset of S cross T, right? Because f is a function from S to T, right? The first set in the Cartesian product is the domain of the function. Second set is the codomain of the function, right? So graph of any function, graph of such a function is a subset of S cross T. So for each, what is the equivalent condition, right? In terms of graphs, for each y in T, whenever we have a point, right, taken from T, there is at most one x in S such that the corresponding pair, right, x is taken from the first set here in the Cartesian product, y is taken from the second set, right? X is taken from domain, y is taken from codomain, remember, right? Such that x comma y is in the graph, right? Is an element of the graph, the subset graph, which is the graph of f, right? A subset of S cross T, G sub f, right? So this is how we check one-to-oneness by analyzing the graph of a function, right? If the graph of a function satisfies this property, then that means it's one-to-one, right? For each y, we must have at most one x, so that x comma y is in the graph, is in the subset G sub f, right? Okay, so this is how we define it, right? This is how we define one-to-oneness, different descriptions, right, of a one-to-one function. Actually, to check one-to-oneness, we can use horizontal test. This is what we call horizontal test. This is some test like a vertical test. Remember, vertical test is used to understand whether the given subset of S cross T is a function or is a graph of a function, right? Horizontal test is used to decide whether or not a given function is one-to-one, right? So horizontal line test. This is used. This is used given a graph, you can use this test to understand whether or not that graph belongs to some one-to-one function. Right? So this is used to understand a given graph belongs to understand if a given graph, maybe I should add here if a graph, let's say, just if a graph belongs to a one-to-one function or not, one-to-one function or not. Okay, so this is why we use this test. Okay, the test is very easy. Look, for each y, right? If I draw a horizontal line in S cross T space, right? Usually we will have, right? Our function will be defined on subsets of real numbers. So usually we have horizontal lines, right? And domains, right? Horizontal axis, right? Containing the domain of the function, and vertical axis containing the codomain, right? Okay, or the image of the function, right? So whenever we draw a horizontal line, it should intersect the graph of the given graph at most one point. At most one point. If it intersects in more than one point, that means there are two x values right in S, right? For instance, x1, x2, right? So that we have there are corresponding pairs in the subset, right? x1 comma y, x2 comma y, right? If we can find such a horizontal line, that means your graph is not one-to-one. Let me state this precisely. A graph is one-to-one, right? A graph belongs to a one-to-one function, or a given graph is the graph of a one-to-one function, right? A graph, a given graph, right? A given graph is the graph of a one-to-one function if and only if, you can just say if and only if, this is how we apply this test, all right? Or just if it's enough. Or maybe I can write if and only if. Okay, if and only if the following is true: any horizontal, right? Any horizontal line, any horizontal line. Horizontal line here means a line parallel to T, right? A line parallel to T. A line parallel to T in a line parallel to a copy of T, right? A copy of T, right? In S cross T space, right? Usually, remember, S and T will be subsets of what? Real numbers, right? Okay, so it's like R square, R cross R, right? So this is a copy of horizontal R, right? I will draw the picture, right? If and only if any horizontal line, a line parallel to T in S cross T, right, intersects the graph, right? Maybe I should give a name for this graph. Okay, let me give a name for this graph. A given graph G, a given graph G is the graph, right? Is the graph, a given graph G is the graph of a one-to-one function if and only if any horizontal line, a line parallel to T in S cross T, intersects G at most, right? Um, at most, right? At most, intersect in at most, right? In at most 1 point. Okay, so this is what we call a horizontal line test, right? Okay, here an example. Actually, I will give examples later, detailed examples. But let me picture this, right? So, for instance, here in this example, let's say this is our f, right? And this is some graph. Sorry, this is some graph. Is the graph? Let's check. Yes, the vertical line test tells us this subset of S cross T. Here, in this case, both S and T we consider as the copy of real numbers, right? So this is our S, this is our T, right? So this thing is really a graph, right? So this thing is really a graph because it vertical line test. If we use vertical line test, it tells us what? It tells us any vertical line intersect, right? The graph, right, at a single point. So by vertical line test, we know that this curve, right, this subset of r cross r, right, is a graph, is a function. But is this function one-to-one? Let's try to understand. Let us apply the test. Any horizontal line, right? Any horizontal line, in this case, for instance, this horizontal line, right? This intersects the graph, and if it intersects at most, right, 1 point. Yes, this horizontal line, this is a copy of. I wrote a parallel. This is horizontal line, a line parallel to S. Sorry, this is some mistake. Of course, T here, the vertical, right, axis, parallel to S. Please correct this. Okay, let's correct this. A line parallel to S is a horizontal line, right? A line parallel to S is a horizontal line here. For instance, this horizontal line intersects here at most 1 point. Another horizontal line, for instance, this one intersects here, right? At most 1 point. Another thing, if you choose another horizontal line, all the horizontal lines in S cross T intersects the graph at most 1 point. Therefore, this is if I say this is the graph G, right? Therefore, here G is the graph of a one-to-one function. Is the graph of a one-to-one function, and we apply horizontal line test. So let us abbreviate this HLT, right? Horizontal line test, and we apply horizontal line test here, right? On the other hand, let us consider another graph. For instance, this, right? This is a copy of R again, copy of R, right? Again, S and T are considered to be S and T considered to be copy of real numbers, right? Real lines. Okay. First of all, vertical line test tells us yes, this subset of S cross T is a graph, right? Is a function. In other words, is the graph of some function, right? So this subset of S cross T, right? Here S cross T again R square, right? So this is a graph, definitely. Is this graph? Question is, does this graph belong to some one-to-one function? So let's try to understand. So if I draw we again apply horizontal line test, of course. So for instance, if I draw this horizontal line, which is a copy of S, right? Parallel copy of S. Yes, it intersects the given thing, right? So this is G, right? This is our G. Right? No problem here for this horizontal line. Another horizontal line, again no problem. Okay, right? Horizontal line, again it intersects in at most one point. But here, for instance, if I draw this, suddenly we realize this horizontal line intersects the given thing in 2 points, right? More than 1 point, right? Or this one, look, or this one. This one intersects at in 3 points, right? In 3 points. So, and then here, for instance, again 2 points. Here again 2 points, right? But it is enough to find a single horizontal line intersecting the given subset in more than 1 point, right? If you can find such a line, then you can immediately conclude, this is if and only if, remember, these are logically equivalent, right, statements. So if you can find just a single, because it says any horizontal line must intersect in at most 1 point. Since we can find, for instance, take this one, or take this one, or consider this one, right? Any of these actually shows that what? Shows that this subset, right? This graph cannot be the graph of a one-to-one function. Yes, it's a graph. It's a graph of some function, but that function is not one-to-one. Okay. For instance, let us consider these two, right? For this y here, there are two x values, right? X1, X2, and these are distinct elements of S. For these distinct elements, their images are the same, right? So it violates this condition. We have two distinct elements, but their images are the same, right? So this y is what? Y is on one hand this is f of x1, but on the other hand this is f of x2, right? Two distinct elements of S is mapped to the same element. So this condition fails. Therefore, by just looking, for instance, these 2 points, right, we can conclude this function cannot be one-to-one, right? And in terms of horizontal line test, right, if you use horizontal line test, basically this means that, for instance, for these choice of points, what is the corresponding horizontal line? This horizontal line, right? This horizontal line intersects the given graph in more than 1 point. Therefore, by HLT, this graph is not the graph of one-to-one function. So G is not a graph, is not the graph. It's a graph, but the function is not one-to-one, right? Does not represent, right? Does not represent one-to-one function. Does not represent a one-to-one function. Yes, it is definitely a graph, but it's not. It is the graph of some function which is not one-to-one, right? So G does not represent a one-to-one function again by HLT, right? So this is how we can apply this horizontal line test. Okay, let's now see more terminologies. Definition. We will define onto function. The meaning of onto, right? We say a function is onto if the image of the function is the entire codomain, right? So given f, let's say it is from S to T as usual, right? S is domain, T is codomain. Such a function is called, we say that, let me write like this, we say that f is onto, or f maps S onto T, okay, onto T, if image of f is exactly T, right? This is how we define an onto map, right? We say f is onto, in other words, f maps S onto T if the image set of f is the whole codomain T. Right? This is how we define onto map. In terms of graphs, we have the following. I mean, we have the following equivalent condition. F maps S onto T if and only if, right, some equivalent description of an onto map, right? If and only if for each y in T there is at least one x in S such that the image of x is y, the chosen element from T, right? So let me write this. So for each y in T, right, there is at least one x in S such that the image of x is y under F. In other words, x comma y is in the graph of, right, is an element of the graph of the function, right? So this is how we can check a given map is onto or not by just by looking at the graph, right? Its graph. We defined one-to-one map, onto map. Finally, let us define also what happens if we have both, right? What we say F is a one-to-one correspondence if it is between two sets, let's say S and T. We say a map F between S and T is a one-to-one correspondence if it is both one-to-one and onto. In other words, a function, let's say F again, from S to T, right? S is domain, T is codomain, right? So a function that is one-to-one and onto, both one-to-one and onto, both one-to-one and onto, right? Onto means, of course, the image, right? The image of F is the entire codomain, right? This is the meaning of ontoness, right? Remember, a function which is both one-to-one and onto is called one-to-one correspondence. One-to-one correspondence. Okay, this is how we define one-to-one correspondence. Or simply we can write one-to-one correspondence. And we can abbreviate one-to-one like this as before, right? Okay, so this is how we define a one-to-one correspondence. Equivalently, right? Equivalently, in terms of graphs, right? Again, in terms of graphs, we have, in terms of graphs, we have the following. F is a one-to-one correspondence, right? F is a one-to-one correspondence. If and only if, right? What is the condition in terms of graphs? For each y, right? Like in the previous, right, condition, for each y in T, for each y in T, first of all, for the ontoness, there must exist at least one such x, right? But since it is also one-to-one, right, the number of such x's must be at most one. Therefore, there must exist exactly one x in S such that xy is a subset of the graph, is an element of graph, sorry. So for each y in T, there exists, or there is exactly one element, right? Exactly one x in S, exactly one, right? Exactly one x in S, such that the pair, right? Like here, the pair xy is an element of the graph of the function, right? If this condition is satisfied, right, f is a one-to-one correspondence. This is how we can check one-to-one correspondence by studying the graph of the function, right? Okay, by analyzing the graph of the function. Okay, let me give some examples. For instance, okay, let us use some Venn diagrams. This function, look, let's say we have a set S, right? In all these examples, we have, I will draw some Venn diagrams, right? Okay, let's say this is T. Let's say S has 5 points here in this example, right? And T has 3 points. T has 3 points. Look at the following arrows. So the arrow indicates, so there is a map here, right? So we have a map F from S to T, and this map F sends, for instance, this element to that element, this element to, for instance, this element. These 3 elements, let's map all to the same element here in the set T. So all these last 3 elements, they are mapped to the same point, right? So this is a first of all, is this a function? Let's see. Yes, it's a function because all the elements, first of all, they have images in the codomain, right? And each element here of S is mapped to unique elements, right? So there is assignments are unique, right? This goes to only this element. This element goes to only this element. So since assignment is unique, so this is a function. Okay, is this function one-to-one? No, because these two distinct things, right? So this is like x1, x2. They are distinct element of S, but they have the same images, right? It violates the condition in definition of one-to-one function, right? So this function is not one-to-one, but it is onto, because all the all for each element of T, there exists at least one element of X such that X comma Y, right, is in the graph. Or in other words, any element of T is the image of some element of S, right? So this is onto but not one-to-one, right? This is onto, not one-to-one, and it's a function, right? This is a function, of course. Let me give an example of a one-to-one function. Let's say I'm going to give an example of a one-to-one function which is not onto. Okay, so let's say we have 4 elements like this. Okay, let's send this to here. Again, we have some function, right? Some function f, some other function f. This element goes to this one. This element goes to that one. For instance, this one, and this goes to, for instance, that one. Okay, is the function? Is this a function? Let's check first. All the elements of S, right, have image values. Okay, first condition. Second condition, assignments are unique, right? I mean, this point goes to that point. This point doesn't go any other point, right? So each point has for each point S, for each point of S, we have a unique assignment. Okay, so that means f is a function, definitely. But it is not onto, right? Because this element, right, if you choose your y, right, to be this, there is no x in S such that its image is that element, this element y. So basically there are, if you can see, there are some elements which are not the images, right, of a point from the domain, right? That function is not onto, but this function is one-to-one. This function is one-to-one because for each, right, element of T, there exists at most one element, at most one, right? So that the element you have is the image of the image of the element of that element of S, right? So this is one-to-one, but not onto function. Okay. Let me draw some one-to-one correspondence. So this is one-to-one correspondence. This, for instance, this is one-to-one correspondence. This time, of course, if you have one-to-one correspondence, number of elements in the domain and codomain, right, must be the same, because one-to-one correspondence, the meaning of one-to-one correspondence, right, for any element of S, right, there is a corresponding element, right, in T, or if you go, you can go also in the other direction. For any element of T, there is an element, right? So it is both one-to-one and onto, right? So for instance, this is such an assignment, such a map, such a function. This goes to here, this goes to here, and let's say this goes to here, right? So all the elements of T are the images of elements of S, right? And no two elements are mapped to the same element of T, right? No two elements of S are mapped to the same element of T. So therefore, this is one-to-one, right? So it is both one-to-one and onto. In other words, it's a one-to-one correspondence, right? Both one-to-one and onto. In other words, this is a one-to-one correspondence. One-to-one correspondence. Okay. And finally, let me give an example which is not a function. Okay, so let's say this is our S. This is our T. Okay. Let's say this goes to here. Let me send like this. Okay, so this goes to, for instance, here, and this goes, let's say, here. Why not, right? This is our function. Sorry, this is our assignment, but this is not a function. Maybe I write here f, but this assignment is not a function, right? Not a function. Why? Not a function, because look at this element. This element, we assign two distinct elements of T, right? Okay, so f, this mapping sends this element to that element of T, but also the other element of T, this element of T. Therefore, this assignment is not unique. Therefore, this cannot be a function. Okay. Okay. So these are some discrete examples. Let us now see some other example. In this example, we will calculate things. So this is more algebraic example, right? Instead of Venn diagrams, we will show show our claims by calculating things, right? So let us prove the following. Prove that the function f is a linear function, the linear function. Linear function means it's a polynomial function. We will see there. We will define these later in full details. But linear function means it's a polynomial function of degree 1. These will be very clear later, right? So let me just skip the definition and let me just call it linear function. But basically the idea is it is some polynomial function, and it has the highest degree, right, of a variable appearing in the rule of the function is 1. In other words, for instance, let me give the function. Our function here is the following, defined by f of x equals 2x minus 3, right? This function. Prove that this function is a one-to-one correspondence. Is a one-to-one correspondence. So that means we need to show f is one-to-one and onto, right? Okay, so let's prove this. To check one-to-oneness, to check f is one-to-one, right? To check f is one-to-one, need to show the following. To check f is one-to-one, need to show that, right? If remember contrapositive, right? Equivalent condition, right? The equivalent condition, which is the contrapositive of the condition appearing in the very first example definition of one-to-one function. What was the you can say x1, x2. Okay, let me do it by labeling in the same way as how we did in the definition. We need to show that whenever f of x1 equals f of x2, where x1, x2 are are real numbers, right? Whenever this happens, then x1 must be x2, right? So we need to show this. This is what we need to show. Need to show this. Here x1, x2 are real numbers, of course, right? The domain and codomain, they are both real numbers, okay? So let's show one-to-oneness. For that, right, so let x1, x2 are two real numbers, right? Let x1, x2 are two reals such that this is true. In other words, they have the same image values, right? They have the same images. In other words, f sends them to the same real number in the codomain space, right? Which is another copy of real number. Okay. So so this means what? This means, okay, let me use this symbol. This is very useful, right? So this implies what? Since we assume they have the same values, let us use the definition of the function. So that means 2x1 minus 3 is equal to 2x2, right? So whenever we see x here, to find f of x1, we should replace x with x1 in the rule, right? What is f of x2? We should replace x with x2 in the rule of the function, right? This is the rule defining our function, okay? This is the rule defining our function. So 2x1 minus 3 equals 2x2 minus 3. But this implies we can add plus 3 to both sides. If I add plus 3 to both sides, we have still equality, right? So but what is left here when we add plus 3's, right? When we add 3's to both sides, we have 2x1 equals 2x2, right? You see, these are logical implications, right? Logical implications. So this equality implies this equality. This equality implies this equality, right? this equality implies what? Now this time we divide by 2. If I divide by 2 both sides, if two things are equal, right? Dividing by 2, we get again the resulting things, they will be still equal to each other, right? But if I divide with 2, then we have what? 2's cancel, of course. x1 equals x2. You see? We get the conclusion here, right? So whenever f of x1 equals f of x2, we prove that x1 must be equal to x2 though. That means f is 1 to 1. So hence, remember this simple. Hence, f is 1 to 1. Okay? To check f is onto, right? F is onto means considering this codomain, we claim that f is onto, right? In other words, we need to show image of f is equal to whole real numbers, right? This is what we need to show. So to check f is onto, right? To check f is onto, need to show that any real number taken from the codomain, right, is the image of some real number under taken from the domain R under F, right? This is what we need to show. Need to show that any real number here, right? Maybe I should just write. Right? I should just write. We need to show that for any, right? For any y in R, right? There is at least one x, right? There is an x in R such that y is the, right? This y taken from the codomain, right? Is the image of x under F. This is what we need to show. Okay, this is the condition that we need to check for ontoness, right? Here, this is what we need to check for one-to-oneness. This is what we need to check for ontoness. Okay, so let y be such an element. So let y be any element taken from the codomain. Okay, we want to find some x so that the value of x under F is the element y that we pick, right? So this is like just a game, right? So we first start with this equation, right? When y is equal to 2x minus 3, right? So is there any x so that, right, this is the value of f, right? The value of x under F, right? Is there any x so that the value of that x under F, which is 2x minus 3, is equal to the element that we pick from the codomain, right, of the function? This is the question. Is this can we find such x? Right? So that means if we can solve this equation for x, yes, we can find. If we can solve this equation for x means if we can so this will prove indeed if we can solve this for x, this will mean that there is some real number, right? And the image of that real number will be what? Will be the element, will be the real number that we pick at the beginning. So let's try to solve. Can we solve this for x? This equality, right, defines y in terms of x. Question is, starting from this equality, can we get some other equality describing x in terms of y? In other words, can we solve this equation for x? This equation is given for y. Can we solve it for x? This is the question here. If we can, yes, the function is onto, right? Okay, so put y equals 2x minus 3. Then let us add plus 3's to both sides. So adding 3 to both sides gives what? Let me first write right hand side first. So 2x minus 3 plus 3 is just 2x is equal to y plus 3, right? Y plus 3 gives this. But this implies what? This implies, now can we solve this for x? Yes, if we divide by 2, right? If we divide by 2, I can just solve this for x, right? Resulting equality describes x in terms of y. In other words, by dividing by 2 gives x equals y plus 3 over 2. And you see, y, for any real number y, this is a well-defined real number, right? Okay, so so this is a real number, well-defined real number. So for any y, right, for the chosen y, right, we have some x such that the value of this, right, the image of x, of this x under f is exact y. Let's check this. So adding 3 gives this. Then maybe I should write then. Maybe I should say observe, right? Observe f of x. What is f of x? So we have this, right? We have this. This is a real number. What is f of x? F of y plus 3 over 2. What is f of y plus 3 over 2? What is the rule of f? Remember, 2 times, right? 2 times whatever inside we have. The inside thing in this case, y plus 3 over 2, right? We replace x with y plus 3 over 2. So y plus 3 over 2. Don't forget we have minus 3 here. So of course these two cancel each other. So it is y plus 3 minus 3. But 3's also cancel each other. So it is just y. You see, we found some x. Whenever y is given, there is some x in the domain, so that its image is the number y that we pick at the very beginning, right? So this tells us what? This tells us f is onto. So hence f is f maps R onto R, right? F is onto. That is, it maps R, domain R onto codomain R, right? In other words, equivalently, it maps R onto R. Equivalently, image of f is R, which is our codomain, right? Image of f is R, which is the codomain. Right? Codomain is the same as image. Maybe I should just leave it like this. You understand, probably. Okay, so so it is onto, right? It is onto, right? It is onto. What is the final conclusion? Hence, right? This is the very final conclusion. Since f is one-to-one and onto, f is a one-to-one correspondence. F is a one-to-one correspondence. This is the end of the proof, right? So we just verified that the function we have is one-to-one correspondence. In pictures, okay, this is some additional, right, thing. So what we did here, let's look at together. Let us graph this function. What is the graph of this function? This is x, this is y-axis. This is a copy of R. This is another copy of R, right? This is a linear function, as I said. If we have a linear function, its graph is a straight line, right? What kind of straight line we have? Maybe you should remember this. Maybe you may remember this from high school, right? Slope is 2, and y-intercept is minus 3. So slope is 2. So this is something like that. Let's say this is right. So this is minus 3. When y is 0, this is y, right? So y equals, when y is 0, x is 3 halves, right? So this is 3 halves. This point is 3 halves. Right? This point is 3/2. This is -3. Slope is slope is what? Slope is 2, right? This straight line is right, has slope 2. Okay. And this is an infinite line, of course, right? This is an infinite line. It goes forever, right? It goes forever in both directions, right? So this is the graph, right? So this is what this is. Whenever we have x here, right? Whenever we have x, right? What is the image of this under our function, right? So this is the graph of f of x. What is f of x? It is 2x minus 3. Whenever x is given from the horizontal copy of real line, which is the domain, right? This is the domain of f. Domain of f. What is the corresponding image? So we have this is y, right? So this is 2x minus 3. This is y. In other words, the point, corresponding point on the graph, right? This is the graph of f, by the way, right? This is the graph of f. This line is the graph of f, graph of our function. Okay, so all right. So what is the corresponding point on the graph? If we have x, y coordinate of the point on the graph, it should be 2x minus 3 because this is the graph of f, right? So 2x minus 3. So this is the graph of our function, okay? So what we verified here, remember, f is a one-to-one correspondence. So this is the domain, and this is the image, right? So this is onto, right? So it's a one-to-one correspondence means the image of the function, right? Image set of the function is the same as the target or codomain, right? So this R is indeed image of f, right? The image of the function is this vertical copy of real line. Okay, here what is happening here? So this is what I'm emphasizing here. This set is the domain, right? This is the domain. This is the domain set, right? So the function f is a one-to-one correspondence between two copies of real lines. So let me use green, right, to highlight the codomain. But codomain will be the same as image. Okay, so this is like some geometric understanding of one-to-one correspondence, right? Okay, whenever we have a point, this x is any point on this red line, right? Horizontal copy of real line. Whenever we have a point, there's a corresponding point, right? One can find the corresponding point by following the graph, right? So whenever we have x here, just draw a vertical line segment so that we have the corresponding, right? So these are verticals, right? These are vertical, and this is horizontal. So whenever x is given from the domain, just follow through the graph of the function. So we have a point on the graph, right? This point is x comma 2x minus 3, and then follow the horizontal line, right, intersecting the vertical copy of real numbers, right, perpendicularly, right? So we have a point. So for any point x, we have a unique point here. You see, whenever we have a point, whenever we pick a point from one of the lines by following, right, with the help of the graph, right, we have the corresponding unique point. You can go also in the reverse direction. For instance, whenever let's say this point is given, look, whenever a point given on the vertical or red copy of green copy of real numbers or real line, right? Can you find the unique point on the horizontal copy of real line? Can we find by following the graph, of course, right? Through the graph of f. Let's see. We cannot go this direction because there is no graph here, but this time, if we have some negative number in the vertical line, right? So we go in this direction. So we have a corresponding point, right? And then we follow what? We follow some vertical line to get a unique point. You see, this point gives that point, right? So for any point, choosing any of these lines we can find a unique point on the other line. This is the geometric meaning of one-to-one correspondence. All right. Okay. I think this is enough for this lecture. See you later. Bye.